So we were talking about the game of contributing to a public good. So that was the game. Each agent had a certain amount of wealth. So the wealth of agent I was denoted with WI. Each agent decided on how much to contribute for the public good. We talked about these last lecture, so I'm going to go fast over it. First of all, we restricted ourselves to a two-player case. So each agent, as I said, had a wealth denoted by WI, a positive number. So he or she had to decide on how much of this wealth to contribute for the production of a public good, and the rest he was going to spend on private good. So his strategy set was the closed interval from 0 to WI, whereas strategy CI and SI denoted the amount that agent I was going to contribute for the production of the public good. We assumed that agents' preferences have the following numerical representation. So when agent 1 contributed C1 units, agent 2 contributed C2 units, the total contribution for the production of public good was C1 plus C2. And the agent, we assume that agents have quasi-linear preferences in money spent on private good. So VI C1 plus C2 denoted the payoff, the utility that agent I gets from the consumption of the public good. And minus CI, that's, well, normally we would write WI minus CI, that's his spending on private good. But we know that preferences are invariant under monotonic transformation. So we said, let's just keep things simple and write it off this form. And what did we assume about VI? VI, a function from R to R. We assumed is differentiable. Increasing. And strictly concave. Now, because of these conditions, UI is differentiable. Sum of two differentiable functions is differentiable. Is strictly concave. Sum of a strictly concave function and a concave function is strictly concave. Well, it might be increasing on the whole domain, or it might be increasing to a certain point and decreasing from that point on. So we can't say anything about it's the sum of an increasing function and a decreasing function. So we don't know about, well, what we know is it might be increasing up to a certain point and decreasing afterward, or always increasing. Okay, so that's what we know. Last lecture, we also noticed the following property of this function. So let me write that for U1. U1. So C1 plus C2, 0 was equal to V1, C1 plus C2, 0 minus, there's no 0 there. V1 of C1 plus C2 minus C1 plus C2, right? Okay. But this is also equal to U1 C1 plus C2. Okay. So if I move this to this side, plus C1 minus C1 minus C2, so that cancels out. So what we see from here is U1 C1, I'm sorry, that's comma, U1 C1 comma C2 is equal to U1 C1 plus C2, 0. Agent 1 contributes C1 plus C2. Agent 2 contributes nothing, plus C2. Okay, so that's what we had last lecture. I moved this to the other side, plus C2. Okay, so far so good? Now, what is the importance of this simple-looking proposition? Well, it says that when I'm looking for best responses of player 1 to some strategy of player 2, if I know the behavior, his best response to this function, I can easily deduce the behavior to, if I know his best response to 0, I can easily deduce his best response to C2. Okay? Actually, at the last minute, we draw the graph. So let me just draw it simply. So if this is U1 of C1, 0, okay. So what would be the graph of U1, C1, C2 look like? Well, we talked about this last lecture. So this is essentially this part with C2 equal to 0. So what it says is shift this to the left by C2 units because of that plus C2. Okay. And then we add C2 to the function, which means that shifted up by C2 units. So what we get is something like this. Okay? Okay? So the shifting up part is not that important for us, but what you should notice is, so every point goes to the left by C2 units and up by C2 units. Okay? So the important thing is, for example, what happens to the maximizer of this function? So what is the relation between the maximizer of this function, that is the maximizer of U1 given C2, and the maximizer of U1 given that the second player plays 0? It's smaller. How much smaller? It will be exactly shift by CT units, right? We just take this graph, shift it to the left by CT units. Okay? Of course, there's something that we have to be careful, which is, sorry? Is positive. So if the peak was, if C2 is too large, if the shift is to the left too much, okay, then you will have a picture which I'm not going to shift it up. The up part doesn't change the maximizer, so let me just shift it to the left. So if we have a shift like that, the maximizer moves all the way here. So what can we say about the maximizer? The best response of player 1 to C2 prime? It's going to be 0 because he's not allowed to pick negative contributions. Okay? Okay? So far, so good? So far, so good? So There are certain things that we have to be careful about, but what this essentially says is that if I know the maximizer of this function over r plus, I can find the maximizer of this function over r plus. Okay? So far, so good? So far, so good? Okay. By the way, last lecture, let me just repeat that fast. We noticed that the strategy set of each player is compact and convex, and the preference of the agents have a numerical representation which is continuous in both components and quasi-concave in C1. Well, if it's strictly concave in all variables, it's strictly concave in C1. If it's strictly concave in C1, it's quasi-concave in C1. So we know that this game has a Nash solution. The problem is, can we find it without knowing the exact form of V1 and V2? Okay? Okay? So, what can you say about the best response of player 1 to C2? What can we say about this? So look at the picture. By the way, pictures are powerful tools, but you have to be careful. You know, there are infinitely many possibilities. A picture is just one instance of all those infinite possibilities. Let's give everybody a minute to think about it. What can you say about the best response of player 1? What can you say about the best response correspondence in general? So let's give everybody 1 minute to think, and then you can discuss with each other if you like. So we have at least 2 ideas so far. Well, wait a minute. Let me first repeat the first part. So your friend says that because the function is strictly concave, we can find the maximizers of this function by taking the partial derivative of u1 with respect to c1 and equating to 0, right? Because the function is strictly concave. Actually, from the strictly concaveness, what conclusions can we have? One of them is what your friend suggested. The other one is there's only one best response. A strictly concave function can have only one maximizer. Okay? Okay. So what does this imply? First of all, if there is a maximizer, it's unique. That is, if there is a best response, it's unique. It can change with C2, but given any C2, if player 1 has a best response to C2, it is unique, and we can find it by taking the partial derivative of u1 and equating it to 0 and solving for C1, right?
Except if it's negative, then it's going to be 0.
What's negative? If what's negative?
If the maximizer is negative.
If the maximizer, the point where the first derivative is equal to 0, if that's negative, it means that the best response is going to be 0. What else can we say? It can't be bigger than? Well, the best response cannot be. So for the sake of simplicity, let's first assume that there is no bound on what player 1 can choose. Let's say that there is no bound on C1. Okay? Because, by the way, what your friend said, you know, equated to 0 works, okay, when the set is, the domain is an open domain. Okay? The derivative, the condition where at a maximum the derivative, the partial derivative, the gradient is equal to 0, only works at an interior point. Okay? So you could have a maximizer on the boundaries where the derivative, the partial derivative, is not equal to 0. So for now, let's assume that there is no bound on the strategies. There's no restriction on the strategies of player 1. We will play that well, okay? So if we can solve the general problem, we'll just put a restriction. If the maximizer is bigger than, so if W1 is here, the point where the first derivative is equal to 0 is bigger than W1, then the best response is W1. Otherwise, the best response is the point where the derivative is equal to 0, okay? Anything else that we can say? Yes? The maximizer must be?
In the form a constant minus
The constant, so what is the constant?
maximizer of the gain minus
Exactly, so find the best response to 0, and you'll find the best response to C2 by shifting it by C2 units, okay? And then, but when you put the restriction that it should be a number between 0 and BI, we should take the maximum of 0 and that number. We'll write them formally, okay? So you see, the picture tells us quite a bit, okay? Okay, pictures together with the properties of the function tells us quite a bit, okay? So, but all these will be true if the function has a maximizer. Are we guaranteed that the function will have a maximizer on R plus or on R? No, so we're initially talking about, so think about UI, C1. Let's take the other strategy to be 0. That we can think of that function from R plus to R plus. Okay, so it's not compact. Okay. It need not have a maximizer, right? But if it doesn't have a maximizer, what can we say about this function? It's always increasing, okay? So if it's, so let's go step by step. If U1, so let me put it this way, does not have a maximizer over R plus, then what can we say about the best response of player? Well, let's go step by step. Then U1, 0 is increasing, strictly increasing. In C1, right? Which means that, which implies B1 of C2 is equal to what? B1 of C2 is equal to what? So what are we looking for? We have an increasing function, and we're maximizing it over the interval 0, W1. It's going to be W1. Okay? So far, so good? Yeah. So this is not a very interesting case. Let me keep this. C1, let me call star, is, I'm saying the maximizer because of strict concavity. We know that there's only one maximizer, is the maximizer of U1, C1, 0 over R plus. Then what can we say about B1, C2? Again, let's think simple. See from this picture, if there was no restriction on the domain of the function U1, when agent 2 increases his contribution by, for example, 1 unit, the best response for player 1 is to decrease his contribution by 1 unit, as long as his contribution does not become negative, right? If agent 2 increases his contribution by 1 unit, okay, then the maximum will shift by 1 unit as long as it, so agent 1 will decrease his contribution by 1 unit as long as he doesn't contribute a negative amount, okay? So, given that, what can we say about B1 of C2? First of all, we're not maximizing over R plus, we're maximizing over the interval 0, W1. Okay, which means that our best response cannot be bigger than W1 and less than 0. Somebody was saying something?
C1 star minus C2.
C1 star minus C2. Okay, everybody agree? So it's a set, of course. Best response is a correspondence. It takes strategies and maps it to sets of strategies. So far, so good? It should also have 0 and W1, right? This is a good point to start with. But every time when you write these things, it's a good idea to put the marker, pencil, pen down and ask, does it make sense? There are 2 problems. One, if C2 is too big, this thing can become negative. But it can't be, you know. It's the strategy set of player 1 is restricted by the interval 0, 1. Well, if C1 star is big, after all, C1 star is the maximizer of U1, C1, 0 over R plus, not over the interval 0, 1. If C1 star is too big and C2 is not big, this number could become bigger than W1. But agent 1 cannot contribute more than what he has. So it means that we should make some adjustments. And the adjustments are, so maybe we should consider cases. So if C1 star minus C2 is negative, that is, if agent 2 is contributing already too much, is contributing more than my ideal amount, I'd rather sit and enjoy what is available without contributing anything, okay? So, what else? Then he will contribute C1 star minus C2. Sorry? And if C1 star minus C2 is less than 0, you will contribute W1. Sorry? Oh, is great. Yes. Yes. We shifted more than W1. Yeah. Sorry. Okay? Any questions? That's it. Okay. of course, for player 2, this situation is symmetric. We can just replace all the 1s with the 2, all the 2s with the 1, and we'll get the best response of player 2. Any questions? Any questions? So we found the best responses. What can we say about the Nash solutions? Come on, try to do it fast. Well, this case is easy, right? If both agents, if the preference of both agents are such that they don't have a maximizer over R plus when the opponent contributes 0, the best response of player 1 is W1. The best response of player 2 to any strategy of player 1 is W2. So the Nash solution would be, actually in this case, we have strictly dominant strategies, right? Player 1 has a strictly dominant strategy of playing W1. Player 2 has a strictly dominant strategy of playing W2. But this is a very exceptional, a very extreme case. So let's not worry about this case. It's very trivial. So let's consider the case. So try to answer the following. C1 star is less than W. Can you see from here? W1. C2 star is less than W2. Then what can you say about the Nash solutions of this game? That is, what would you predict that players will play in this game if your predictions was based on the Nash solution concept? Draw a picture first. What would you think the Nash solutions of this game is? How much would player 1 contribute? Well, if you want, let's put it. What do you want to put? Well, start drawing the picture, and while drawing the picture, if you need to put a restriction, then we'll put it. It might be a good idea to just start thinking about this part. This is partially defined, so it makes things complicated. But maybe just start thinking about this part, and then going into these. And this relation is a very simple relation, right? The relation between C1, the best response of player 1 to C2, and C2 is a linear relation here. Okay. So come on, anybody? Can that be true? Start by putting a mark. So, for example, put C1 star somewhere. Can that be true? Look at that. So look at the best response or look at the picture. What did we say? If player 2 increases his contribution by 1 unit, the best thing for player 1 to do is 1 unit what? Decrease his contribution by 1 unit. So if you're increasing your contribution, I will decrease by the same amount as long as I don't contribute a negative amount, as long as I can decrease it. Which means that the best response correspondence should be upward sloping, downward sloping, downward sloping, right? It comes from this picture or also from here, right? So if C1 is an element of the set, it means that C1 has to be equal to C1 star minus C2. That's a linear relation. That's an inverse linear relation between C1 and C2. So you should immediately be able to draw this picture. You have to do these things faster. So I have C1 star somewhere here. It's less than W1. So I'll just concentrate on this part. That's this line. But of course, player 2 cannot contribute a negative amount. Okay. Player 1 cannot contribute a negative amount. Moreover, player 2, actually, let me draw it a little bit bigger so it's more visible. Okay. Moreover, player 2 cannot contribute more than W2, so I don't have to worry about the best responses of player 1 when C2 is bigger than W2. So somewhere I should put W2. Okay? For now, let me just put it here. So in a way, I already assumed that W2 is less than W1. So that's what we have. We're done. Right? If W2 was larger, actually let me draw that part. What would the best response correspondence look like? So this part is not meaningful, right? Then this comes into play. So the best response correspondence of player 1 would look like this. So that's the picture of B1. So add to this the picture for B2. So this time we have B2 of C1 is equal to C2 star minus C1 if C2 star minus C1 is between 0 and W2. So wherever I see a 1, I make it a 2. Wherever I see a 2, I make it a 1. So again, this time I'm going to draw this. Again, the relation is a linear relation, so it's a line. Actually, it's an inverse linear relation, so it's a line with a negative slope. So somewhere when C1 star is equal to 0, okay, this best response is C2 star, so I have to place C2 star somewhere. By the way, because the slope is minus 1, this point is C1 star. So let's assume C2 star is less than C1 star. Then it will go down like that. But negative best responses, negative strategy is not meaningful. So actually, this part is governed by this relation. And then this part is governed by this relation. So if this is the case, if both C1 star and C2 star, C1 star is less than W1, C2 star is less than W2, and the way we draw this picture is C2 star is less than C1 star, then what can you say about the Nash solutions of this game? Yep. That's, by the way, C2 star. The graph, which graph? This one. This is B1, best response, the graph of the best response for player 1. This is C1 star minus?
C2 star is positive, right?
C1 star minus C2 star, according to this picture, yes, it is.
So it means that C2 star minus C1 star is negative, which means that the best response of the...
Wait a minute, C2 star minus C1 star is? C2 star minus C1 star is negative, yes.
The best response of firm 2 should be 0.
Of firm 2, and that's what we have when the strategy of player 1, okay, is in this region, okay, the best response is 0. So put C1 star here, it's negative, the best response is 0. So take the strategy of player 1, the best response of player 2 to the strategy is 0. That's why we have this red line, which corresponds to this. Okay? So far, so good? Yep. No, not really. You see on the picture, there's no such assumption. So this can go up, down. In terms of what am I see? Mm-hmm. What should go up to W? So this is W2. Okay. So player 1 chooses a strategy between 0 and W1. Player 2 chooses a strategy between 0 and W2. So by the way, we assumed C1 star less than W1, C2 star less than W2. Now when I was going to draw the best response of player 2, so if there was no restriction, if I was just interested with this part, it's going to be a line like this. So it could be this line, it could be this line, it could be this line, it could be this line. This is the case where C1 star is equal to C2 star, which we should also maybe look into, but it's, you know, if we're thinking about a random population being chosen, you know, the probability that they will have the same maximizer might not be very high, okay? So this is the case where C2 star is bigger than C1 star. This is the case where C2, so again, there's infinite many possibilities. So this is just a frame from all possible frames, okay? So once I drew it like this, I assumed that C2 star is less than C1 star, and which is also less than W1, okay? Well, here I draw it such that, you know, W2 is bigger than C1 star, but I could have done it, you know, I could have, actually, let me draw it on a separate. So actually what I'm going to do is, I'm going to draw this line, C1 equal to C1 star minus C2, and then this line, C2 equal to C2 star minus C1. So this point is C2 star, okay? If C2 is equal to 0, C1 is equal to, this point is C1 star, okay? So now let's put W1, W2. Where do you want me to put W1? Tell me to stop. Here? Okay. Which violates this case, okay? But we can also look, well, let's first consider this case and then we'll look into your case, okay? So I'll go, so, okay? So once I have this, first of all, because of this negative part, player 1 cannot have a negative strategy. Then we have, you know, from this picture, we get that we are in this region. The best response correspondence is marked here. Now let's mark W2. Again, whoops, sorry about that. Let's assume that this condition holds. So I'll start from here. This is C2 star. This is C1 star. So stop here. So that's W1. So what is the best response correspondence of? Yes, I'm sorry. That's W2. Okay? So, it stops here. What about best responses of player 2 to every strategy in this region? By the way, I shouldn't have marked this part. I'm sorry. That ends here. Sorry about that. That's like this. This is B1. What is B2? What is player 2's best response to all these strategies of player 1? It's this line. Okay. So if W2 is less than C1 but bigger than, is less than C1 star but bigger than C2 star, this is the picture we have. If W2 is also bigger than C1 star, then this is the picture. Okay. In any case, what can you say about the Nash solutions? Where does the graphs of the best responses intersect? In this picture, it intersects here. In this picture, it intersects here. So what is the Nash solutions of this game? When this condition holds, again, be careful. No matter what W2 is, no matter what W1 is, as long as C1 star is less than W1, C2 star is less than W2, the Nash solutions will be agent 1 contributes C1 star, agent 2 contributes nothing. Okay? So, two important points. First, even though we didn't know the exact functional form of the numeric representation of the preferences of the agents, all we knew was it's quasi-linear in spending on private good, okay? And it's the utility, I'll call, from consuming the public good is increasing and strictly concave and differentiable, of course, okay? Just with using those facts, we were able to say what the Nash solution looks like. The only thing we don't know is what C1 star is. Well, conceptually we know it, numerically we don't know it. To find C1 star, we need V1. But we do know about the structure of the Nash solution, even though we don't know the exact functional form of U1 and U2. Okay? So that's something interesting. We don't always have to know the exact functional form. Knowing the properties can enable us to say a lot about the Nash solutions, about dominant strategies, and so on. The other interesting thing, so that was on the technical side. The interesting on the economic side is, you see, the only thing we assumed about W1 and W2 was C1 star is less than W1, C2 star is less than W2. The Nash solution is still this, whether, irrespective of whether W1 is bigger than W2 or W2 is bigger than W1. So it's not the rich who contributes to the production of the public good. As long as this condition holds, it's not the rich who contributes to the production of the public good. It's the one who, I will say in quotations, values it the most. That is, who's willing to contribute the most if he or she is the only one who will be contributing. Okay? So C1 star is the amount that agent 1 is willing to contribute if he or she is the only one who's willing to contribute. C2 star is the amount that player 2 is willing to contribute if he or she is the only one who's willing to contribute. Okay? So as long as those quantities are less than their endowments, the agent who values the public good the most will contribute it, irrespective of their wealths. Again, provided that condition holds. And the other player will free ride. Will not contribute anything, but enjoy the public good. Okay? So far, so good? So far, so good. Any questions? I'll leave it as an exercise to you to look at the other cases. The other cases are not that interesting. This is the most interesting, and I'll put in quotations, the most realistic situations. Okay? Any questions?